Okay, so we are considering channel equalization, and I said that there is a line through which binary bits are coming. You can take a blocks of maybe small odd number of bits, one block odd number of bits, next block another odd number of bits, and so and so. So there are 2 to the power odd possibilities, and to every possibility you assign one voltage level called symbol. So there are 2 to the power odd symbols, and the symbol set, all the 2 to the power odd symbols, it is called alphabet. Okay, alphabet. So now every time a symbol is there, we have to send it down a communication channel, a media. But as I told yesterday, all communication channels in the whole world are analog. They can carry analog waveforms. And we can give an analog waveform at the input, it will go through the analog channel and you will get some analog waveform at the output. But they are not, they cannot take discrete things. They are okay, 5 volt, 10 volt, 4 volt, not like that. So therefore, the symbol I have to have some pulse, okay, which will be a basic pulse, and that will carry on its shoulder this information about the symbols. Okay, so I got a symbol sequence IN, element of S, that is I of 0 is the symbol at the 0th symbol period. A symbol period means odd number of bits forming a frame or a block, which is a symbol period. Okay. So I0, then comes I equal to I1, then I2, I3. These are various voltage levels, all belonging to S. So there is a sequence of symbols. Every symbol value I have to send down the line through a pulse. Okay, through a pulse. So the pulse is basic pulse is important because pulse is analog waveform, and this is required because whole world, all the communication channels, the whole world, actually is analog. All the communication channels, all the media, they are like free space or wire, telephone wire, optical fiber, and all these are analog media, analog channels. Okay, they can take only analog waveforms. That is why a pulse is necessary, as I told you yesterday. So suppose there is a basic pulse, we design like this P of t. Pulse is triggered at this point, maybe it attains a peak, something like this here. This height may be 1 and this center point is t. Okay. So, you take this pulse, multiply by say I0, the 0th symbol. So, pulse remain as it is, his height will be multiplied by I0 into 1, so I0, all right. Then what happens? You trigger the same pulse after some time, maybe tau, and then that will be multiplied by next symbol I1. Then after 2 tau another pulse will be triggered and again multiplied by I2 and like that, and through the channel the superimposition of these pulses will propagate, right. So, you will have things like this, one pulse, its height is I0 and I should measure the pulse when it is highest, so capital T. Then just after maybe tau amount of time, next symbol comes. So, symbol period is tau. Every tau amount of time, maybe nanosecond or whatever, a new symbol comes. So, at 0, one symbol came I0, I trigger a pulse, multiplied it by I0. So, the pulse shape remains same, only amplitude changes from 1 here to I0 here. Then next symbol period, when the next symbol comes after one symbol period, that is tau, same pulse is triggered, multiplied by the new symbol which is I1. I0 is done, now next is I1. So, it could be something like this. This height is I1. On the other hand, before this I0 was triggered, before that I had tau amount of time earlier, at minus tau another pulse was triggered, and that could have been multiplied by I minus 1 previous symbol. something like this. So, this is I minus 1 and so on and so forth. Okay. There will be more pulses to the right, more pulses to the left, they may have some interference here. Okay. And theoretically all of them have, but practically as you go further to the right, further to the left, pulses situated far to the right, far left, they will not have overlap here, they will not be able to interfere here. Nevertheless, now the superimposition of all these waveforms is a waveform which goes through the channel, and at the receiver I first measure the height of the waveform amplitude at t, assuming I get I0, then at tau time to the late, after tau, t plus tau, I measure again, I expected to get I1, or at minus tau, I sample again, I expected to get minus 1. So, 0 at t plus tau, t minus tau here, tau to the left, okay, because tau is the symbol period. Capital T is the peak of one pulse. Next pulse, its peak will be shifted by tau, because it was triggered tau second or tau nanosecond later. The pulse to the left, it was triggered minus tau at minus tau time. So, obviously, its peak will be not at capital D, but t minus tau. So, I will be sampling at t minus tau, at t plus tau, t plus 2 tau, like that, and I would expect to get I minus 1, I0, I1, I2, I3 dot dot dot. But that will not happen here, because you can see, even though I have I0, the pulse from the right, pulse from the left, maybe some more pulses from the right, some more pulses from the left, they all will interfere here. So, I will have not only have I0, I will have this much contribution and this much contribution, and like that. This contribution from right pulse. 1 minute. This much contribution from the right pulse, and this much from this left pulse. So, they all get added. As a result, I will not get I0, I will get other values here, okay, which is called inter-symbol interference. How much is the value? How much this blue colored height? If from the peak of the pulse you go tau to the left, whatever is the pulse width. So, t, so if you go here, t minus tau, okay, the same pulse, but now its height is multiplied by I1. So, we will get a component, additional component I1 and p capital T minus tau. Similarly, this pulse, from its center point, if you go tau to the right, so if you go tau to the right and multiplied by I minus 1, you will get another component. So, from the center point to tau to the right here, okay, because in the center point next peak is tau to the right of this peak of this pulse, they are separated by tau. So, they will all get added. So, they are coming from other symbols I1, I minus 1, I2, I minus 2 and all that. So, this will give rise to error, and that this is called ISI, inter-symbol interference component. Okay. To avoid this, first we should design the pulse in a suitable way. We design so that when the one pulse, maybe the white color one, has the peak at time equal to t, the pulse to the right, it should go through 0. Okay, so, it will have 0 interference. Pulse to the left, it should also go through 0, and so and so. That means, this pulse should be such that if I go tau to the left from the center point, like from the center point of this, the center point where the peak is located, if I go tau to the left, this blue curve should go through 0. That means, the basic pulse p t minus tau should be 0. Then if you have another pulse, that is its peak will be shifted, I mean by 2 tau amount, because from this point capital T, if you go tau to the right, you get the peak of the immediate right pulse. The next one, its peak will be at capital T plus 2 tau. If that also should not interfere, that should also go through 0 here, and so on and so forth. So, t plus tau, t plus 2 tau, t plus, okay. So, this pulse, consider this, from its center I go tau to the left, it should go to 0. The one which is further to the right, from its center if I go 2 tau to the left, it should go through the 0, and like that. That means from capital T, if I go tau to the left, 2 tau to the left and all that, there is p t minus any k tau, okay, that should be 0. And if I go tau by the same way, if I go like consider the red colored pulse, from the center if I go tau to the right, I am here, that should be 0. So, it should go through 0, basic pulse should go through 0 if from the center point if I go tau to the right, it should go through 0, or if I take the one further to the left. So, its peak is at t minus 2 tau. Okay, so, from that peak if I go 2 tau to the right, that pulse should go through 0. So, that is why we do like this. Okay. And at the center point it is 1. So, this is called zero forcing condition. Okay. Pulses which satisfy this condition called Nyquist pulses. Okay. Example, sig. Sig pulse. So, at capital T, you have a peak so this point is t plus tau. This point is t plus 2 tau, this point is t minus tau, and like that. Next is this is t minus 2 tau, like that. So, sig pulse. A more popular waveform of this kind similar to this is called raised cosine, and I am sure you have studied this in your undergraduate, raised cosine pulse. Otherwise, just take a basic book on communication, they will tell you about the pulse, raised cosine pulse. So, all these pulses satisfy zero forcing condition. Zero forcing means I am forcing the pulse to go through 0 after certain, at certain points, certain sampling points, like at t plus tau, t plus 2 tau, t plus 3 tau, or t minus tau, t minus 2 tau and all that. So, I am forcing it to go through 0. So, zero forcing condition is imposed, and if the pulse satisfies this, it is called Nyquist pulse. Fine. So, I suppose have a Nyquist pulse, okay, and I have apparently no problem. But so suppose your PT or Nyquist pulse. But the channel through which it will pass, it is not an ideal channel. Channels are usually not ideal channel. Ideal channel is such which will pass all frequencies present in the input signal equally okay, and if it delays, it will delete all frequencies, so by the same amount. So it is actually something like this: h e to the power j omega. Ideally, it should be 1. Okay, and its angle, you can change the magnitude. Its magnitude should be either 1 or some constant k for all frequency, and the phase angle will be a constant, a linear function of omega, like some k omega, maybe like this. Okay, some k omega. K is a negative number, k omega. Then it is an ideal channel, because if you pass a signal through it, there will be no distortion. You can easily see what is h to the power j omega for any omega. What is h to the power j omega? It is the magnitude times e to the power j angle, and this is constant, maybe a, and this is e to the power j k omega, right. So, therefore, if input some x t, they are all analog signals now, x t, which has Fourier transform x j omega, or I am using, sorry, I have changed the notation, but this is more used in DSP. Let me call it this. Because these are analog channels, so I should have here also. Magnitude and angle. So, it is k omega. So, if input is this, output will be we know output y t, that is at the output of the channel or at the input of the receiver. You will receive a wave from y t, which has Fourier transform this. That is nothing but input Fourier transform times this. So, a to the power j k omega, and you know from your signaler system that if a Fourier transform is multiplied by e to the power j k omega in time domain, it amounts to a shift by k, delay by k. So, it will be, so y t will be nothing but a as it is, x as it is, but it will not be t, it will be t plus k, and k is a negative number, that is why I gave a downward slope. So, actually it will be delay, which is fine. If I get a positive slope, say k equal to plus 2, then y t will be x t plus 2, which is not possible, because that makes it non-causal. At standing at time t, you have information about x t only, not x t plus 2. So, you cannot generate a system whose output is x t plus 2, a future output, future input. Okay. That is why in all practical circuits and systems, you find phase response to be having a negative slope, never positive slope, because negative means it will be a negative number, it will be it will be causal, which is practical. Anyway, these are some side inputs I try to give to my students, okay, as an additional knowledge item. Anyway, so suppose this is the, what is happening, this kind of channels, if it is x t input, okay, same x t just multiplied by capital A. So, it does not distort the waveform, also delayed by k. So, it is just delayed and amplified, but basic waveform does not change, and that is why it is an ideal channel. All right. So, if the channel is ideal, waveform does not lose its step, maybe maybe it gets amplified and delayed a bit, but from channel measurement I can find out what is A, what is K and all that. So, I can make the corrections. So, no problem. But unfortunately, in the whole world, all practical communication channels between say from free space communication between antenna to antenna, or say telephone wire, okay, or optical fiber, or fluid like water, all that through which underwater communication takes place. All these have channel response which is far away from being ideal. Magnitude response will be very jittery, it will be varying with omega, phase also will not be linear. So, altogether it will distort the waveform. That is, actually if you have h omega this, for an ideal channel the impulse response will be, you put here impulse response will be A delta t plus k. Delta is the Dirac delta function. Delta t has got Fourier transform 1. If it is t plus k, it will be e to the power j k omega times 1, and A remains as it is. K is negative, and therefore, in time domain, if you have a signal x t that will be convolved with this, but A will remain as it is, x t convolved with delta t plus k will give you x t plus k. So, there is no change, x remains x, only delayed or advanced whatever, okay, delayed because k is negative. But in a practical channel, h t will not be like that. It will not be like A times an impulse. This means an impulse, Dirac delta impulse at t equal to minus k. Okay, it will not be so. It will be h t will be rather, impulse was, what I was trying to say is this, ideally h t is maybe at k, at minus k, and k is negative, so minus k is positive, so it will be like this. So, it is an impulse which is fine, k is negative, so that is why it is coming on this side, because this impulse is at t equal to minus k, but k is negative means actually some plus value. All right, this is t. This is ideal case, but this does not happen in practice. Rather, h t will be some waveform like this. So, convolution of this with x t will distort your x t heavily. It will no longer have the same shape as x t. Therefore, even if you take a lot of care to design your Nyquist pulses which satisfy the zero forcing criteria, as it goes through the channel, it will lose its shape. So, it will not follow the zero forcing criteria correctly. It might be close to that if the channel is not that bad, but it will not, and as a result inter-symbol interference will still come back at the receiver input, and that is what we have to remove, and it is removed by a device called equalizer. Okay. So, to carry it further, suppose P t Nyquist pulse transmit pulse. P t, as you go through the channel, analog channel, real life, there is analog. This basic pulse which was satisfying Nyquist condition, that is this zero forcing condition, it will go through this. After convolution, it will be distorted, it might become p prime t, and it will be not Nyquist because it is distorted. So, zero forcing criteria will not be satisfied in general, though it might be close to this, because channel may not be that bad, but therefore, your inter-symbol interference will come back. Okay. So, what will happen is this, you will receive something like this. At capital T, you will be sampling the received waveform, this is the received waveform. sampling capital T at capital T to look for symbol I0, then at capital T plus tau to look for symbol I1, at T plus 2 tau to look for symbol I2 dot dot dot. So, in general at T plus n tau, you have this pulse which is no longer Nyquist, it might be like this, some pulse. Okay. So, it will be, its height will be what? The basic, this pulse p prime at capital T multiplied by I n, this is the nth symbol, n tau. So, I n times p prime, if you consider the basic pulse, its center point is at capital T where it is peak and I am measuring there. So, p prime capital T value of this distorted pulse, which is not 1 anymore, that times I n. So, this is what I will have here. Then maybe from the left hand side, so there will be a component here. Okay. What is that component? Again the same p prime T pulse center point here. Okay. And if I go tau to the right, so this much is the basic pulse p prime from T to tau to the right, this much height times that symbol here, which is I minus 1. This much will come as interference. Then this one from a center point, if I go tau to the left, whatever is the value that is multiplied, I am talking the basic pulse, that is multiplied by the symbol I n plus 1, sorry, this is n, I am sorry, this is not I 1, I minus 1, it was I n, so it will be the previous symbol I n minus 1, I n, previous is I n minus 1, and now this is I n plus 1, okay, I n plus 1 times, so this much is I n plus 1 times p prime, from the center point you are going to the left by tau, so p prime t minus tau, and dot 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 dot, so on and so forth. So, typically you will have, so when you sample here, the net receipt, the sample, if I call it R for receipt or n, or n, that will be having one term from the correct symbol I n, p prime t, there is a distorted pulse which looks like this, its value at the center point capital T where it is peak, it is supposed to be peak, that is my sampling point in any case, at that point I sample to measure I n. So, there whatever be the value, no longer 1 because of distortion now. So, this is this. Then I have got one set of terms I n plus 1 p prime t minus tau, then further to the right it will be I n plus 2 p prime t minus, if you have another pulse here from the center point I go 2 tau to the left to reach this point. So, the value of that pulse now will be from center point, if you go 2 tau to the left, that value times this and dot 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 dot. Theoretically up to all the pulses up to infinity, that is all the pulses to the right, whatever be the value at this point, that much. But actually in practice these pulses are time bound pulses. So, you do not have to go too far, after some time only, I mean the pulses situated to the right will no longer contribute here, they will disappear. Okay. All right. And then there is one more term from the left hand side I n minus 1 p prime t plus tau I n minus 2 p prime t plus 2 tau plus dot dot dot. Let me give some name to them. Let me call this to be, well, this is a constant, right. Once you have a chosen Pt, this is known to you. If you pass it through a channel, you know what is P prime t, it is a fixed waveform. So, its values at different sampling points are known to you. So, value at capital T, okay. Only thing is the value is not known when the channel is not known, and that is most often the case, but still it is a constant waveform. So, this is a constant. So, let us call it channel constant, let us call it H0, just I am giving a new name, nothing else. Let me call this H minus 1, let me call this H minus 2 and dot dot dot, and let me call this H1, let me call this H2. In this case, the whole summation turns out to be this. So, Rn will be, you can see HR I n minus R from minus infinity to plus infinity. Very easily, if you start with R equal to 0, so H0 In, that is the term you have H0 In. If you take R equal to 1, In minus 1 H1, okay, here H1 In minus 1. If you take R equal to 2, In minus 2 H2 here, and dot dot dot. On the other hand, if you take R equal to minus 1, H minus 1 In plus 1, we have here. Okay. If you take R equal to minus 2, H minus 2 In plus 2, you have here, and like that. But this is nothing but a discrete convolution. So, this is a model. After you sample the waveform, whatever value you get, this is the equation, this is a mathematical model then, okay, of the received symbol in terms of the future and past symbols. Okay. Future symbol is coming, but do not worry, this is not real life in the sense, okay, how the causality is bridged here. It is because causality is bridged because when I sample the current waveform to find out In, by that time I already triggered the waveforms of the future waveform. So, they pass through the sampling point, I mean at the sampling point they already exist. So, they contribute with their values, that is why contribution from future pulses come. Okay. That is, I can trigger a waveform here, but I measure it after some time, and within that time I have triggered several such waveforms, future waveforms. So, they carry information about In plus 1, In plus 2, In plus 3, and they all contribute. That is why contribution from future terms is coming. Okay. That is why I am saying it is not a real life analog system, it is a mathematical equation which we get, which can be said a discrete time model, discrete model of the channel, and that model can be non-causal, but physical region of the non-causality I have already explained. So, I stop here and we carry on from here in the next class. Thank you very much.